So this PPT is going to explain about the counters, especially about the design of synchronous counters. So we already seen the topic flip-flops and what is shift register and what are the types of shift register. Now the counter operation. So counter is also a group of flip-flops connected together, but it will perform the counting operation. Counting operation means it will count the clock pulse in the way it will increase the count. For example, 2-bit counter na it will increase the count from 0, 1, 2, 3. It is a 3-bit counter na the maximum value is 111. So it will start the count from 0 to 1, 2, 3, 4, 5, 6, 7. And similarly, if it is a down counter na, down counter 3-bit na, it will count the clock pulse. The value, the maximum value is 7. 1, 1, 1, 1, 7, 6, 5, 4, 3, 2, 1, 0. So we have up counter as well as down counter. So mainly we were classifying the counters, okay, depending upon the clock how we were applying. It is asynchronous and synchronous counter. So this PPT is mainly concerned with the synchronous counter. So synchronous means, the meaning of synchronous means the common clock pulse will fit to all flip-flop. So the similar way common clock pulse will be given to all the counters. Asynchronous counter means the common clock pulse will not fit. The output of one flip-flop will be given to the pulse of the next flip-flop in cascaded. So that is asynchronous counter. And so we will broadly classify according to the pulse asynchronous and synchronous counter, or else it will counting on the process up counter or down counter, or sometime it will count only the particular count. For example, depending upon the state. For example, if it is a mod 5 counter means it will count till 5 only. Mod 6 counter means it will count till 6. Mod 12 counter na it means count 12. So depending upon the types of clock pulse, synchronous and asynchronous, depending upon the counting operation up counter or down counter, depending upon the number of state, it will be the modulus counter. So in this PPT we are going to see 2-bit, 3-bit, 4-bit counters, whether it may be up counter or down counter. And then we are going to see one example in modulus counter, and any counter can be asked, binary to gray counter or so these are the counter plot we are going to discuss in this PPT. This is the design of 3-bit synchronous up counter. So here 3-bit synchronous up counter means we require 3 flip-flops. So we are going to use T flip-flop. So 3 flip-flops are required. 2-bit synchronous counter na 2 flip-flops. 4-bit synchronous na 4 flip-flops. Okay. So there are 5 steps are there to design a synchronous counter. First step is we have to draw the state diagram. State diagram means from what is the first stage and what is the next stage. For example, up counter na 0, 0, 0. The next stage is 0, 0, 1. The next stage is 0, 1, 0. Then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, then 0, 0. This is up counter. So first we have to draw the state diagram. Then second we have to draw the excitation table. Then third we have to draw the circuit excitation table. Fourth, K-map. Fifth, diagram of the counter. So 5 steps. First step is state diagram. Excitation table is second step. Third step is circuit excitation table. Fourth step, K-map reduction. And fifth step, we have to draw the diagram of this counter. That is using flip-flop. So 3-bit synchronous up counter. First we have mentioned the state diagram. So 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. I think you have seen the state diagram which mentioned here. Okay. Now excitation table. Excitation table is explained in the flip-flop. So this is for T flip-flop. Qn means present state. Qn plus 1 means next state. T is value. So 0, 0 na the value will be 0. 0, 1 na 1. 1, 0 na 1. 1, 1 na 0. So this is like if you want to remember, I can say one thing. It's look like an XOR table. So you can remember the excitation of table of flip-flop. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. I think flip-flop we have explained. So there we have explained the excitation table. Okay. So now we are going to see the circuit excitation table. The third step. First step, we have written the state diagram. Then we have written the excitation table for T flip-flop. Then the circuit excitation table. It's very simple table. In this tabular column, QC, QB, QA. It's a present state. QC star, QB star, QA star. It's nothing but the next stage. TC, TB, TA. That we have to refer that excitation table and we have to write. So you just look up this QC, QB, QA 0, 0, 0. What is the next state? 0, 0, 1. Then you come to the second column, second row. 0, 0, 1. What is the next stage? 0, 1, 0. Come to third column. 0, 1, 0. What is the next state? 0, 1, 1. Then you come to the fourth row. 0, 1, 1. What is the next state? 1, 0, 0. Then you come to the fifth state. 1, 0, 0. What is the next state? 1, 0, 1. 1, 0, 1 is the present state. Then what is the next state? 1, 1, 0. 1, 1, 0. The present state. Now what is the next state? 1, 1, 1. 1, 1, 1 is the present state. Now what is the next state? 0, 0, 0. So up counter means it counting my clock pulse from 0, 1, 2, 3, 4, 5, 6, 7. So we are saying present state is 0, next state is 1. Present state is 1, next state is 2. Then present state is 2, next state is 3. So 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, again 7 to 0. Okay. Now how we have to write the TC, TB, TA value? You have to go to the previous slide. You have to refer Qn and Qn plus 1 and then we have how we have written the T value. So already the excitation table we have seen 0 0 na 0, 0 1 na 1, 1 0 na 1, 1 1 na 0. So similarly you look up here why I am going to write the value for TC. You see QC and QC star value 0 0 na 0. Then you write the next TC value. You have to write TC, you have to refer QC and QC star value. To write TB, you have to refer QB and QB star value. To write TA, you have to refer QA and QA star value. So 0 0 na 0, 0 0 na 0. Okay, again 0 0 na 0, 0 1 na 1, 1 1 na 0. Can you understand or not? So refer QC and QC star, write TC values. Refer the tabular column. QB and QB star na TB value. QA and QA star na TA value. After writing this, you have to go for K-map reduction. Now this problem comes under 3 variable K-map. QC, QB, QA. Okay. So I have to write for TC1 K-map, TB1 K-map, TA1 K-map. It's a 3 variable K-map. So you have to take QC, QB, QA and write the TC value here. And then you have to go for the reduction. I think the reduction we have given in a K-map here. So TA is equal to 1, TB is equal to QB and TC is equal to QA into QB. Okay, have you understand? So this is the way we have to write the K-map reduction. Okay, so after writing this K-map reduction, then we have to go for the logical diagram. That is flip-flop diagram. It is 3-bit synchronous up counter. So while we are drawing 3-bit synchronous up counter, we are know it is a 3-bit na 3 flip-flop is required. So TA should be connected with 1, TB should be connected with QA and TC should be connected with QA into QB. And it is a synchronous counter. So fed common clock pulse to all the flip-flop. So you see the diagram, TC is connected with 1 and TB is connected with QA and TC is connected with QA into QB. So QA into QB definitely which gate I require? And gate I require and then I have to connect with TC. And QA, QB, QC are my outputs. We all know it will start from 0, 0, 0 to 1, 1, 1. So if I connect this way, I will get my 3-bit up counter. 3-bit down counter na same way. 5 steps. State diagram, excitation table of T flip-flop. Then the third step is circuit excitation table, K-map, 4th step. And 5th step, this flip-flop diagram. Okay, you'll get the same diagram, but in this way you'll get it in reverse. What we will do now, TA is 1, TB is QA bar. Okay, TC is QB bar into QA bar. If you derive like the same derivation, you go through this, you get the 3-bit synchronous down counter with TA is 1, TB is QA bar and TC is QB into QA bar. That's it. The next we will see will be synchronous counter up counter. Okay, so I think state diagram, transition table, it takes much for 4-bit synchronous counter. So I think we need not to draw anything. We can directly draw the diagram and the truth table. Okay, and we all know while we are drawing 3-bit synchronous counter, we have understand TA is connected with 1, TB is connected with QA, TC is connected with QA, QB. That's it. 3-bit is same. So 4-bit nothing but TD will come. 4th flip-flop will come. That should connected with QA, QB, QC. That's it. Can you understand? So 3-bit what we have drawn, the same thing. The 4th bit what we have to draw QA, QB, QC. Okay. So the diagram we have given, but here you see we didn't draw for the T flip-flop. We have drawn for the JK flip-flop. Okay, and we all know the JK flip-flop and T flip-flop will be same way. That is nothing but when J and K is shorted, that is nothing but T flip-flop. Okay, so what you have understand now? Here also the same thing. TA is 1 now. J is 1, K is 1. Okay, TB is nothing but QA now. JB is equal to QA and KB is equal to QA. Okay, then the third flip-flop, TC equal to QA into QB. Now, similarly for the third flip-flop, JC equal to KC equal to QA into QB. Here TC is equal to QA, QB, QC. Now, here JC and KC is equal to QA into QB into QC. So J and K is nothing but when I connect J and K, the input will be a single input, that is T. So don't confuse JK and T. The circuit diagram will be same way, but T means we will get only a single input. J and K means 2 input, but the connection is similar to T. So I have to, how we will connect? You just see the diagram of this up counter. Here J and K, it is connected to logic 1. Okay, and just you see JA and KA is connected with QA. And JC and KC, that is the third flip-flop, which is connected with QA and into QB. And you come to the 4th flip-flop, JD and KD, which is connected with QA, QB and QC. So this is the way. So draw the diagram and then we have to draw the truth table. So this is the diagram of synchronous up counter. I told you, I already mentioned, by using J and K as a 2 inputs, I can use as a T as a single input. That is the only difference between JK and T flip-flop. J and K is shorted, we get the T. So here JA and KA, first flip-flop, J and K is connected to 1, and flip-flop B, J and K is connected to QA. And third flip-flop, J and K is connected with QA and QB. That's why they used AND gate. And in 4th flip-flop, J and K is connected with QA into QB into QC. So this diagram states that for flip-flop A, JK connected with 1, flip-flop B, JK connected with QA, flip-flop C, JK connected with QA into QB, and flip-flop D, JK connected with QA into QB into QC. This is 4-bit synchronous up counter truth table, and you can see that value will vary from 000 to 1111. So you can understand that my value will vary from 000 to 1111. That is, by applying each and every clock pulse, the bit value get increased by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the value get increased till 15. This is a diagram of 4-bit synchronous down counter. Flip-flop A, J and K is connected with 1. Flip-flop B, J and K is connected with QA bar. And flip-flop C, J and K is connected with QA bar into QB bar. Flip-flop D, J and K is connected with QA bar, QB bar, QC bar. So 4-bit synchronous down counter. So my value will start from 1 1 1 1 to 0 0 0. By applying the clock pulse, it will be decrement the operation. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is the way it will decrement the counting operation. So up counter, that we have seen the diagram 2 slides before. So this is the down counter diagram. So here we have to write the truth table in a way, such way it will decrementing the operation. So this is a synchronous up slash down counter. It's a 4-bit synchronous up slash down counter. Here 4 flip-flops have been used. So 4 flip-flop, the JK flip-flop has been used. So in up slash down counter, up slash down means if the value is 1, then automatically it will do the up operation. If the value is 0, automatically it will do the down operation. So here the 4 gates were connected. By seeing this operation, the upper AND diagram will do the up counting and the lower AND diagram will do the down counting operation. So it's we have already seen the same concept. J and K is connected with 1. It is up. J, K connected with QA, it is also up operation. J and K connected with QA into QB, up operation only. J and K connected with QA, QB, QOC, up operation. So successive flip-flop, this is the way they will connect. In down counter, reverse operation. JK connected with 1 and the next flip-flop JK connected with QA bar, and in third flip-flop JK connected with QA bar, QB bar, and in fourth flip-flop JK connected with QA bar, QB bar and QC bar. Now in this slide we are going to see design a mod 6 synchronous counter. Okay, so mod 6 synchronous counter, now you have to do this mod 6 synchronous counter. If the question is not so specific, design mod 6 counter, now you can design synchronous or asynchronous counter. Okay, asynchronous counter is nothing but a ripple counter, that will be explained in the next PPT. So this entire PPT is about synchronous counter. So synchronous counter, I already told what is the procedure. First draw the state diagram, then write the excitation table of the flip-flop, and the third you have to draw the circuit excitation table, then the K-map reduction, then finally we have to draw the flip-flop diagram. So 2-bit na 2 flip-flops, 3-bit na 3 flip-flops, 4-bit na 4 flip-flops. Okay, so we have seen 4-bit synchronous up counter, down counter, 3-bit up counter, down counter, and this is mod 6 counter. So mod 6 counter always do the upper operation only. So but in the state diagram we have to draw only the 6 changing state. So my mod 6 counter means 0 0 0, then 1, then 2, 3, 4, 5. So I am getting how many states? 6 states. So for this 6 state I have to draw the diagram 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1. So this is the diagram. So what is my maximum value? 1 0 1. So 1 0 1 now how many bit is there? 3 bit is there. So 3 bit now how many flip flop is required? 3 flip flops is required. Okay. So we have decided 3 flip flops are required. So now you draw the state diagram, then draw the excitation table. In the excitation table, QC, QB, QA is written. QC plus 1, QB plus 1, QA plus 1 is written. So now from that we have to write JC, KC, JB, KB, JA, KA. I already told, don't confuse on JK flip-flop or T flip-flop. JK na 2 inputs, T na single input. So if J and K is connected, that is we can say T flip-flop. So both are same only. Okay, so we have written the excitation table. So here we were seeing the design 6 mod 6 synchronous counter. So design a mod 6 synchronous counter, we have understand that how we have seen with this diagram. So first we have drawn the state diagram, then we have written the circuit excitation table from the excitation table of the JK flip-flop. Then we have to go with the K-map reduction. So in the K-map reduction, JC, KC, JB, KB, JA, KA. So we have to draw 6 K-maps, but it is a 3 variable. So we have to draw 6 3 variable K-maps, and then reduction technique is same what you learn in the second unit. So similar way you reduce it, applying the conditions, and you find out the values. After finding out the values, we have drawn the logical diagram, and using the logical diagram we have implemented the circuit. So this type of question they will ask in the 16 mark question. So design synchronous counters will be mainly asked in part B questions. So study well all these slides. Thank you, students.